of chemostats, but before we do that, we'll do what I promised in the last class, which is a brief review of the history of reactors, chemical reactors. So, if you look on the screen here, that the history of chemical reactors, is essentially talked about this. So, chemical reactors are of three major kinds. So, the batch reactor, the history of that is started at the dawn of human civilization with process of cooking and so on. The second one is the plug flow reactor, which started in the late 18th century. Then a big conceptual leap. So, the plug flow reactor was being used from the late 18th century, and so essentially the major difference between a batch and a plug flow is that you had continuous inflow and outflow in the plug flow, whereas in the batch you just had to put the things in and wait for how long the reaction took. So, the reaction could have taken a day or 2 days and still you have to wait to get the products, whereas in the plug flow reactor you have a continuous inflow and outflow. Now, a big conceptual leap came in the form of a CSTR reactor, which sort of combined the advantages of the batch reactor with that of the plug flow reactor. The advantages of the batch reactor is it's a easy portable vessel, whereas the plug flow reactor is a long tube and it's hard to carry from one place to another and stuffs like that. So, that was the advantage of the batch reactor. The advantage of the plug flow reactor is its continuous inflow and outflow. Okay. So, these are the two advantages. So, the CSTR model, CSTR thing, what it did is combine the advantages of the batch, the portability and the fact that it requires less space of the batch reactor with the advantage of the plug flow reactor, which is the continuous outflow and inflow. And this was, remember, not at some point of time was discovered things. So, this was not there before that, and this came in 1908. I said this just in the last class. This was discovered by two German scientists, Bodenstein and Wolgast, okay, in 1908. It turns out, so this is a big conceptual leap as far as the whole idea of chemical reactions and chemical reactors was concerned, okay, because as I said, it's portable, it takes less space, and at the same time it has continuous inflow and outflow, and that kind of revolutionized the whole chemical reactor, the whole chemical industry. And if you now look at chemical industries, almost all chemical reactors are CSTRs, or continuous inflow, continuous stirred tank reactors. Only a few percentage of them, a small percentage of them would be batch reactors. Now, 1908, it turns out, is a very eventful year for the history of chemical engineering or chemical reaction engineering, because you had the tubular reactor model, the plug flow reactor model rather, and in 1908 again it was Erwin Langmuir who founded the flux type boundary condition, okay, what is now was known as Danquist boundary condition, but it is no longer known because there are difficult problems, issues there. So, as I said, that Langmuir he got the Nobel Prize later because of his work with the kinetics, the Langmuir kinetics, adsorption kinetics, but this was another of his path breaking findings, the flux type boundary condition. The reason being, for us it might seem very mundane at this point of time to think of a flux type boundary condition, but think of it when somebody was discovering it 100 years back, to come up with the concept of that, the fact that whatever is coming in through convection at one end equals what is going out because of convection and diffusion at the other end is quite a leap. The reason being that the concepts of convection and diffusion were not as properly underlined at that point of time. Okay, it was only underlined around 1937, and I come to that paper which dealt with that. But so that there is a little bit of fuzziness around these concepts of convection and diffusion, and to come up with a boundary condition in 1908, which has stayed for more than 100 years now, and nobody has proved it incorrect yet, is quite a conceptual leap. So, that was done by Langmuir in 1908. So, and so that's a very, very important boundary condition, and it came to be later known as the Danquist boundary condition, which it should not have been, but we did some unraveling of the real history behind this. So, it turns out that after Danquist, this condition, this Danquist boundary condition, not Danquist, let us call it the flux type boundary condition, was rediscovered a few times. So, the first time it was rediscovered by Förster and Geib, two more German scientists in 1934, okay, and maybe it's not really rediscovered, maybe because Bodenstein and Wolgast wrote their paper in German. So, Förster and Geib would have read those papers most likely, 1934. Then it was again rediscovered by Gerhard Damm-Kohler, another of the most famous chemical engineers along with Langmuir, I think he's probably the most famous chemical engineer of his times and our times. So, he rediscovered it in 1937. It was not rediscovered actually. What he did was, this is a landmark paper, the 1937 paper of Gerhard Dammkoller, and it was published in German. And what he did in this paper was, he reviewed like we are reviewing the whole history of chemical reaction engineering in 1937 paper. He reviewed the entire history of chemical engineering, including Langmuir's work and Förster and Geib's work, and the whole history of Bodenstein and Volga's discovering the CSTR. He reviewed the entire work of chemical reaction engineering that was available till that point of time. Okay. Then Danckwerts rediscovered, and he was truly trying to rediscover, trying to show the world that he discovered it, because he did it. See, there is a fundamental difference between what Dammkoller did and Förster and Geib did and Danckwerts did, because Förster and Geib and Dammkoller, they referred to the earlier papers of Langmuir and showed that they have discovered these boundary conditions, whereas Danckwerts buried everything. He buried all of the previous work, and he pretended that he had discovered the boundary condition, and that pretension worked really well, because these papers of Förster and Geib and Dammkoller were all kind of buried by the political events of the time, which was the Second World War. So, because there were Germans, and there was an enormous amount of hatred against Germans at that point of time, and the whole world opinion against Germans at that point of time. So, their works were lost. Nobody was reading and the German science, nobody was paying any attention to them. So, their works were practically lost, and then Dammkoller in 1953, he sort of claimed to rediscover the boundary condition, and now it has been unearthed much before. It was not us, but around 20 years back it was been found that Danckwerts didn't discover this boundary condition, and people stopped calling it the Danckwerts boundary condition. They just and there is enormous confusion, whether you want to call it the Langmuir boundary condition and Förster and Geib boundary condition. So, just people decided to call it the flux type boundary condition. Okay, but if I think I wrote it in the last class, but I'll write it one more time. Yeah. So, the boundary condition simply goes as, so whatever is coming in U times C equals whatever is, so U times C in equals whatever is going out minus D times del C del X. Okay. So, you have the tubular reactor over here, and you are trying to find out, this is X equals 0 at, so you are trying to find out what is the boundary condition at X equals 0. So, this is my boundary condition. So, whatever is coming in at this point is because of convection, U times C in. Okay. You can call it even U in times C in, but U is supposed to be the same on both sides. So, U times C in coming in because of convection equals what goes out because of convection, U times C minus plus what goes out because of diffusion, and the diffusion term is minus del C del X. Okay. So, this was essentially the flux type boundary condition, and we still continue 100 years down the line, we still continue to use this boundary condition, and it's a quite phenomenal and path breaking boundary condition. So, if we are trying to write something like if you a second order differential, we will come to that, but if you are writing a second order problem, then you need a second boundary condition. So, what would be the boundary condition at the other end? So, X equals 0, this is my boundary condition. What would be then my boundary condition at X equals L? It would be, typically it would be del C del X equals 0. Okay. Why? If L is large as compared to, say, the radius of the reactor. So, if the length is very large, what does this mean? What means is that all the reactant has reacted and there is no reactant left at the end to leave. Okay. This means that all reactants have reacted. Okay. So, there is no reactant left. So, these are the boundary conditions. Anyhow, so let us go back to the history. So, then again, as I said, the 1937 paper of Gerhard Dammkoller, that was one of the most important papers in the history of chemical reaction engineering, and it's a two-dimensional convection diffusion reaction equation. So, he for the first time wrote the two-dimensional convection diffusion reaction equation, and this paper was written in 1937 in German, and then it was later translated into English. And what are other things he did, and let's recount, because so in this paper he introduced the idea of radial and axial diffusion. So, just as I said, the whole ideas of different kinds of diffusion and convection were not very clearly outlined way back in those days, and it was Damkohler who first introduced the idea of radial diffusion and convection diffusion, axial diffusion, and how they are different. So, it was not really understood at that point of time how the radial and axial diffusions are different. Then he introduced the parabolic velocity profile. Till then we had a plug flow reactor, right, plug flow reactor model, PFR model. What does the PFR model entail? It means that the velocity profile is flat within the reactor, and but the velocity profile is not really flat, because when you have flow inside the tube, the velocity profile is parabolic. But if you understand that in a plug flow reactor there is no way, I mean there is difficulty at least to introduce a plug flow radial velocity profile. Let me show you why. Because what you have is U del C del x equals minus R of C, right. This is your plug flow reactor model. Now, this is in x, right. So, this is my reactor, and this is the x direction, and this is the R direction. Now, if U equals U naught 1 minus R over R square, then it's how do you solve it? So, if I put it back over here, 1 minus R square over R square equals R of C, how do you solve it? You see what I am trying to say? The difficulty of solving it. Why? Because the differential in the x direction, and then you have a term in the radial direction. So, how do you solve it? There is no way to solve it. So, the only way of being able to incorporate a radial velocity profile is to actually go for a two-dimensional description. So, which is what Damkohler did. He went for a two-dimensional description, and as a result of which he could incorporate the parabolic velocity profile. He included radial and axial diffusion, and he included the flux type boundary condition. So, it was the first time somebody looked at the chemical reactor in a very comprehensive way, incorporating convection, radial and axial diffusion, parabolic velocity profile, as well as flux type boundary condition, which includes both convection and diffusion effects at the entrance. Okay. So, this was a 1937 paper, and then the whole idea, you are aware of the idea of residence time distribution theory, right. So, surface renewal and residence time distribution theory. So, they came around like the same time from Dankwert's paper, but again it turns out that the Forster and Guy was actually the first one to discover the RTD theory, the residence time distribution theory. The whole idea that that the different fluid elements in a reactor will have different residence times. So, you can say that the reactor residence time is tau, but that does not mean that the entire fluid in the reactor spends the amount of tau in the reactor. What does residence time mean? When I say that the residence time, what does residence time mean? The amount of time you spend here. So, the residence time of a BTech student here is 4 years, or the residence time of a PhD student is 4 years, something like that. Okay. So, which means that the amount of time that you spend from inlet to outlet. But when I say that the residence time in a CSTR is tau, strictly speaking not. So, it was discovered essentially by Forster and Guy that strictly speaking it's not that every element of fluid in the reactor is actually spending the tau amount of time. Okay. So, typically the residence time distribution is goes something like this. So, this is how the residence time changes. So, the average of this, if you take the whole of it and divide it, then the average of it is tau. But some elements, as you see over here, some elements of fluid, so this is the amount of elements of the fluid. So, some elements of the fluid spend very small time, again some very small, so it is a bell shaped curve, and only a fraction say spend a very large amount of time in the reactor. So, when I say the reactor, is this something you have to remember? When I say that the reactor residence time is tau, it does not mean that everything in the reactor spends tau amount of time. It means that the average amount of time spent within the reactor by a fluid element is tau. Okay. So, this whole concept was actually started by Forster and Guy in 1934, and then it was again Dankwerts is a great rediscoverer. So, he rediscovered this theory in 1953, but he had some inputs also, which is he generalized it. It was in Foster and Gibbs paper 1934, which I got translated through somebody and read it, and it was a very localized concept, but Danckwerts generalized it for the whole reactor thing, and it really, his presentation was good. Then so last important things that came in the whole CSTR business was the concept of micromixing, which is mixing at the molecular scale, okay, because reaction takes place at the molecular scale, and if reaction has to take place in the molecular scale, then there has to be mixing at the molecular scale, right, because if A and B two reactants are there, and unless they are mixed at the molecular scale, they cannot react. Is it clear? Because the reaction has to take in the molecular scale. So, the concepts of micromixing, maximum mixedness, and complete segregation when there is no mixing at all between the two components. So, these were propounded by Zwittering in 1959. So, I think that concludes our brief review of the history of chemical reactor models. What we will do now is that so much of this theory, as you see, is related to CSTRs, because as I said, CSTR was a big conceptual leap. So, what we will do now is try and look at the CSTR for bioreactions. So, the CSTR for bioreactors is called Chemostats, okay, and this is a let me show you the picture and try and explain. So, this is the central thing that you have over here is a chemostat. So, it is a CSTR, which means it is a continuous stirred tank reactor, which has two parts, one is continuous, another is stirred, and four parts actually: continuous, stirred, tank reactor. So, the continuous means there is a continuous inflow of feed and a continuous outflow of product. Stirred means it is being stirred by a stirrer over here. Tank, so it is a tank and then it is a reactor. So, the four elements come together. So, as you see that the way it works for the chemostat is that there is a feed reservoir over here, from which feed is being continuously pumped into the reactor. Okay. So, then you have a buffer solution, which is also being pumped, because these are being bioreactions, you have to maintain the pH at a certain value, could be 7, could be 5, could be 6, whatever, but you have to maintain the pH at a certain value. So, you have a pH controller and a buffer solution being sent in. You have air being taken out and replenished. So, those kind of things we have talked about this, you need a certain amount of oxygen into the system and so on. So air being taken out and replenished and stuff like that here, and then the product. So the air taken out here and replenished from here. The sterile air comes in here just for the oxygen that you need to supply, and the nutrient, that is the carbon, hydrogen, nitrogen in liquid form, are a part of the in the feed reservoir itself. So the product is taken out. Now the product will include these three: X, S and F. What is X? X is the cells that are growing, S is the substrate, and feed is everything else apart from the substrate and the cells. So, the part of the feed which is not neither substrate nor cells. V is at any point of time the liquid volume in the reactor. Why is V important? Not the volume of the actual reactor, because the residence time of the reactor, the average residence time as we call it now, depends on the volume of the reactor and not the V. And volume of the liquid, sorry, in the reactor, and not the actual volume of the tank, okay, because the rest of the tank that has the air in it is not of any use. So, so V here, and then the product is taken out and pumped out and put in a product vessel. Okay, so this is the whole flow chart of the system, and is there any question, or do you want me to stop for anything here, or shall we proceed? We should proceed. Okay. So, the next question that comes in is that we have to, in order to understand the dynamics of this process, we have to write balances for this. So, the balance would be straightforward, similar to the CSTR balance that you have written, except that it is for two components here. Okay. So, what are the two components you are going to write the balances for? One, there will be, okay, let us go slowly. So, how many balances do you think that you will have to write? The first balance would be the overall balance of volume, which is the volume accumulated or volume held back in the reactor, and volume coming in and volume going out. So, that is the overall balance. Then what else? We have component balances. So, one would be the substrate balance. So, the two major components, as you can see in the picture over here, that X, S and F. So, one would be the substrate balance S, then would be the cell balance X. Okay. So, essentially three of these. So, let us go and do it. So, the chemostat, as you can see over here, is an ideal CSTR, okay, because it is stirred and everything and continuous and so on. So, the first you need to do is total volume balance. So, the total volume balance is very straightforward, dV dt equals Fn minus F out, the feed coming in minus feed going out. Okay. Fine. So, the next balance we do is a mass balance for the cells, and mass balance of the cells is simply, if you take this for example, you will have to multiply it with the cell concentration. So, ddt of x v, this and these two, plus there will be a generation of cells. Okay. So, that is the only difference between the other component and the cells, is that there is a generation, I mean overall volume is not being generated, whereas cells are being generated. So, ddt of x v equals Fn times x naught. X naught is the amount of cell that is coming in the feed. So, the feed itself can have some cells, minus F out times x, x is the amount of cells that is in the outlet product, and mu times x is a specific, mu is a specific growth rate per unit cell, mu times x is the total for the total amount of cells times the volume, so because the volume of the liquid should come in over there. Equation is death of cells. Yeah, death of cells has not been included, but you can add another term minus beta x, right? We did last time, right? So, you can just add minus beta. So, you can, instead of mu, you can replace mu by mu hat, where mu hat is mu minus beta. Fine, that's straightforward. So, the last thing that we need to do is the mass balance for substrates. Fine. So, which is ddt of Sv equals Fn times S naught minus F out times S minus mu x v over y, because I explained this several times in the last couple of lectures. Y is just the yield ratio of x over S. Okay. Now, typically if you want to typically in a CSTR, what you would like is that the inlet is equals outlet, and if that is the case, Fn equals F out, then dV dt is 0. So, as a result of which the V is a constant, right? And you can do a lot of simplifications in these equations, because V is a constant. You can take V out of this equation, you can take V out of this equation, fine, and you can get rid of V in some of the places, because one of the over V will come in here. So, when you do the simplifications, you get dx dt equals F over V x naught minus x plus mu x. It looks like a lot simpler equation, and just as he said that if you want to include the death of cells, replace mu by mu hat, where mu hat is mu minus beta, beta being the specific death rate of cells. So, and the last thing would be the substrate balance equation for the substrate, ds dt equals F over V S naught minus S 1 over Y mu x, right. So, what would be a step now? So, once we have done this, so what would you like? We like to find out how it would change, but what would be a step? What would do you think we should do now? So, if f is a constant and known, okay, then how many variables do we have? Just two variables, right, and two equations. So, what we intend to do is essentially solve this, but how do we solve this? I mean, what kind of solution do you want first? Let me ask you that. What is that? Possible for what? For everything? well, I don't think analytical solution is possible. One of the things you can try to do is get an invariance. I taught you how to get invariance in the last class. You can get an invariance, and then you can get an analytical solution for a combination of x and s, not for x or s separately. But what we want to do first is a easy step out, which is obtain the steady state solution of it. Okay. So, f over v is called the, so we will do that. So, let us define some quantities first. F over v is called the dilution rate of the cells. Okay. F over v is the dilution rate of the cells, and what is the unit of S over v? F over v? What? Inverse of time, which means it is inverse of the residence time of the system. Okay. So, F over v is 1 over tau, which is the inverse of the residence time of the system. So, when you do that, you can put your ddt and ddt of x equals dilution rate d, instead of 1 over tau in this chapter or in this course, we will use the dilution rate d, so instead of the residence time. So, d is 1 over tau x naught minus x plus mu x, and ds dt is d s naught minus s minus mu x over y. Fine. Now, mu is, we are going to assume a monod growth kinetics. As I said, it is the most popular and most useful growth kinetics. There are plenty others, as I showed you in one of the earlier lectures, but this is the one that we are going to try and use for now. Now, as I said that sometimes I might ask you in the exams, for example, to do the similar kind of thing with other growth kinetics. I can give you more complicated growth kinetics, or I can give you growth kinetics where inhibition is involved, or all other kinds of things possible. But you have to be aware of how is the process. So, what we are going to do from now on, today's class and next class is slightly hard, and you should pay attention to the process, what is really happening and how to do it, because then you should be able to do it for other kinds of systems. So, that is fine, right. So, we put the monod growth kinetics in, and so then we go for the steady state solution. So, at steady state, this is your basic equation. So, dx naught. So, if you look at this here, so we put a steady state out here. So, dx naught equals d minus mu times x, okay, for the x equation, and then similarly for the substrate also you will have another one. Now, the first approximation that we assumption that we make is that it is a sterile feed. Okay. So, we are solving it for a sterile feed. Sterile feed means that there is no cell in the feed that is coming in. It is an assumption, of course, because typically there are cells, but we are just trying to solve it for this system. We will solve it for other systems also without sterile feed, but let us try and solve it for with sterile feed. Okay. Is it clear? The sterile feed means that x naught, there are no cells in the incoming feed. So, when you do that, you simply get d equals mu. Okay. The dilution rate equals mu. Now, mu is a specific growth rate, remember. Okay. So, it goes as mu max times s over ks plus s, which equals the dilution rate. So, if you have a fixed dilution rate, so what this means is, for a sterile feed, for the system to have any sort of meaningful solution, if you have a dilution rate that is fixed, then your steady state substrate concentration has to be this. You see what I am saying? Why is that? Because see, if x naught is 0, then d minus mu times x is 0. What is the solution of this equation? The two solutions of this equation. Okay. One is that x naught, x itself is 0, then the other one is that d equals mu. So, if d is not equals mu, then the other solution is x naught x equals 0, which means that no cells are being produced, which is worthless, because I am running the whole reactor to produce cells, right. So, the only feasible solution in this space is d equals mu. Now, when you put mu max s over k plus s equals d, then SS, the steady state substrate concentration, is dks over mu max minus d. Fine. Okay. Provided that XSS is not 0, I mean, of course, and mu max is greater than d. Mu max has to be greater than d, because you see why, because if mu is greater than equals d, then this fraction over here is always less than 1. So, mu max obviously has to be greater than d, right. So, from the second equation, that is the equation for the substrate, this is what we get, Now, the substrate concentration and d equals mu for x naught equals 0. So, you can substitute back over here d equals mu in this equation, right. So, over here, and then you can get your x, that is a steady state concentration XSS in terms of these as this, because we wrote our SSS before, if you remember in the last slide. I will just wait for a few seconds because some of you are writing. So, and then I will show you if you need to. So, we wrote the SSS in the last slide. So, you can substitute your SSS from the last equation that we wrote before into this, and is it clear to all of you, or do you want me to go through the steps? Okay. So, here all you need to do is let me just quickly show. So, all you need to do, SSS is given here as dKs over mu max minus d. All you need to do is substitute for SSS in from that equation into this equation, and you put d equals mu over here, and then you will get XSS, that steady state concentration of cells in the system goes as, if we forget the y, let us ignore the y, then it goes as S naught minus dKs over mu max minus d. Okay. And this we already did, d max equals mu max d equals mu max S naught over Ks plus S naught, d equals mu max S over Ks plus S. So, d max would be the maximum value that the d can take is mu max S naught over Ks plus S naught. Why? Because the maximum value that the S can take is S naught, the feed concentration. Clear to everybody? If there is any point you need to stop me, please stop me and I will explain one more time. So, if that is clear, then as in this equation, as mu max goes to d, you see over here, then what will happen, this goes to 0, the denominator here goes to 0, okay, and this goes to infinity as a result. So, solutions are possible for d greater than mu max and d less than mu max. Is it clear? See, what did we get from our initial assumption of sterile feed? We got that d equals mu, fine, and one of the things we said is that d is typically, if d equals mu, then d would be less than mu max, right, because mu max is always greater than mu. So, we are actually working in this space of d less than mu max, but just to make sure that to make sure that this is a feasible range. So, d equals mu max, there is no solution because this whole thing blows up. The solution is only possible in the d less than mu max, d greater than mu max, but obviously we are working in the space of d less than mu max. Clear? No confusion, right? So, this is what I said, that we are working in the space of d less than mu max, because it is not possible for d, if d equals mu max mu, then it is not possible for d to be greater than mu max, because mu max is obviously greater than mu. Now, for XSS equals 0, d greater than mu max, which is not in the which is not in the, it is in the feasible range, but it is not of any interest to us. If no cells are being produced, it is of no interest to us. So, this is just another possibility. So, for x is not equals 0, d has to be less than mu max, clear, from not necessarily from the mathematics, but the physics of the problem. D has to be less than mu max, because d is d equals mu, and if d greater than mu max, then XSS is 0. So, my steady state solution is that for d less than mu max, I have my steady state solution as this, and for d greater than mu max, it is 0. Okay. So, what does this mean? What it means is that why am I trying to answer this question? Why am I trying to kind of boil everything down to d and mu max? Both of these two are parameters of the system, d and mu max, but what is the difference between these parameters?
We can change d by
Absolutely, yeah. See, the mu max is a parameter that cannot be changed, it cannot be manipulated, whereas d is a parameter which can be manipulated. D is 1 over the residence time of the reactor. How can I change the residence time of the reactor? Just flow rate, yeah, just basically by changing the flow rate or the volume that of the liquid in the system. So, what this is trying to say is that so what this is trying to say over here is that these two cases, that if you want cells to be produced, your D has to be less than your mu max, or in other words your dilution rate has to be less than the maximum specific growth rate of the cell. If your dilution rate is greater than the maximum specific growth rate of the cell, then there are no cells which are going to be produced. What does this physically mean for you? What it physically means is that if dilution is very large, then it will sweep the cells away, it would take the things away with it. So, if D is very large, for example, then what it means? What it means is the residence time in the reactor is very low, fine, because D goes as 1 over tau. If the residence time of the reactor is very low, what does it mean? It means that the cells are not getting enough time to react for it and grow. Okay. So, this is the physical interpretation. So, in bioreactor system, in biochemical engineering, they say that dilution of the system, dilution rate being very large means that the system is being excessively diluted, and as a result cells cannot be grown. But if you look at it from a chemical engineering point of view, then we convert it into the residence time. So, D very large means residence time very small, which means that the cells are not getting enough time in the reactor to grow. Okay. So, that is why it happens. Now, mathematically, let us look a little bit at the mathematical space of it. So, if this is the case, that is D is less than mu max, then your steady state XSS I just gave you here, this is the steady state solution for the cell, and the first thing here is the steady state solution for the substrate. Okay. Do you need to write the steady state solution for cell? I think you wrote it already, but if you want to, I will give you a few seconds. Okay. So, the steady state solution for the substrate now is given by dKs over mu max minus D. So, this has to be satisfied, S naught greater than dKs over mu max minus D. Okay. So, because mu max is greater than D, so the denominator is positive. So, the second criteria that we get, so there are two criteria that we have to satisfy. One is that the residence time of the system or dilution rate of the system, residence time is 1 over dilution rate of the system has to be greater than mu max, and the second criteria we get is given here, S naught, which is the initial concentration of substrate in the feed, has to be greater than this quantity dKs over mu max minus D. Okay. So, both of these two criteria have to be satisfied in order to be able to produce cells. Okay, so that your XSS is greater than 0. Okay. Both of these two criteria have to be satisfied. Fine. Is it clear? So, both these two criteria have to be satisfied in order for it to be. If they are not satisfied, then XSS and SSS are not in the feasible domain. So, what happened was that if you remember, how do we get the first criteria? We got the first criteria by showing that if mu max is less than D, then your XSS is 0 or negative. We got the second criteria by showing that if your S naught is not greater than this, then your SSS would be negative or 0. Okay. Because see, what happens is that both the substrate and the cell that are coming out have to be positive numbers, both of them, both the substrate. So, for the positivity of the substrate of the cell, you need to ensure that D is less than mu max. For the positivity of the substrate, you need to ensure this quantity, that is the initial amount of substrate that you put into the system, is greater than dKs over mu max minus ds. Okay. And and the second regime is D, no, I don't know, this is a case of XSS equals 0 and SS equals S naught. So, what this means is that nothing is happening in the reactor. Okay. For the same case, but nothing is happening in the reactor. So, which means that you start with cells. This is a, what kind of solution is this? Trivial solution, yeah. So, this is known as a trivial solution, whereas XSS is 0, that is you put in cells, sterile cell, your input solution is free of cells when you are putting it in. So, now no cells in, no cells out, and as a result whatever substrate you put in is whatever substrate that leaves the system. So, this is a trivial solution. Why am I going through this is because one of the things you kind of forget, like let us go back and show you this equation here, for example. So, a system like this, you guys, very calmly you go and write the one single solution that is there possible, but when you are doing a mathematical analysis, you have to take into account all kinds of solutions. So, one of the solution is a trivial solution, and the trivial solution, as you will see a little later, maybe in next lecture, is important also. So, why we are doing this is trying to look at the entire space composed of all different kinds of solutions. So, the first one we discussed is a non-trivial solution, the second one is a trivial solution, and this is a summary of the behavior of the chemostat. So, these are by equations which I am sure you had already written down. So, there is no point spending any more time on this. So, dx dt equals this and ds dt equals this, and mu equals mu max s over ks plus s, and what I will next do is summarize the results also, the ones we looked at. So, this is the feasible range, this is the feasible range of solution here, just as we discussed that there are two constraints for this things to happen. That feasible range means both positive results for XSS and SSS, that is the substrate and the cells going out of the reactor are both positive numbers. So, there are two constraints for this. One is that the dilution rate has to be less than mu max, the second one is the initial concentration of the cell is greater than this number. Now, if any of these two constraints are violated, then what you end up having is a trivial solution, as you have over here. All these are trivial solutions, because XSS is 0 and the steady state concentration of the substrate is same as what you put in. Okay. So, what you need to remember, the best way to remember this is that these two constraints have to be satisfied. If they are, then in this space where both these constraints are satisfied and intersect, you get this solution. Anything else, you get trivial solutions. Okay. So, this is essentially the steady state analysis of the chemostat. Now, what we are going to do is look at, so when you in a chemical reactor or in any kind of continuous reactors, you want to run these reactors at steady states, fine, you would like to. Why do you want to run these reactors at steady state? Because control is easier, because whenever you have dynamics of the system coming in, control gets harder. But what happens in a real system, when we are running it at the pilot scale, or even forget plant scale, even at the pilot scale when you are running, and even in the lab scale, what happens? You are trying to run it at the steady state, but you are probably not able to run it at the steady state. Why does that happen? You can have your controllers and everything, and you will see that when you do even experiments in the control lab, you will see that you are trying to manipulate your control variables so that the system is at steady state, the level of the fluid in a U tube or anything for that matter, and you will see that it keeps oscillating. It is very hard to retain it at the steady state. Why is that? What kind of disturbance? That is right. Yeah. What kind of disturbance? Yeah. The key word here is, as he said, fluctuations, or what we call in mathematical parlance is perturbation. Okay. There are these natural noises or natural perturbations that are there in the system, and why do these natural noises or perturbations come in? From every angle. You think that this table probably has no vibration, but it is full of vibrations. So, wherever you are putting in your reactor has lots of vibrations in there, and these vibrations lead to perturbation or fluctuations in the system. And as it turns out that many of these reaction systems are pretty sensitive. The reason these are sensitive is that I talked about, I do not remember, I think I did talk about the case for the autocatalytic reaction in this class itself, right, at some point of time. So, that one is example of why these systems are very sensitive. The reason these systems are very sensitive is because they are nonlinear. So, when they are nonlinear, so a small perturbation in one of the variables can lead to large perturbations in the entire system, because of nonlinearity there is a multiplying effect. Okay. So, a small perturbation in one leads to another perturbation in the other, and these two effects kind of multiply, and then the whole amount of perturbation that is generated in the system is multiplied and kind of exaggerated. So, so there is a whole analysis for that, and that analysis is known as stability analysis. So, that is the next thing we are going to look at. So, what we are going to do is stability analysis of bioreactors, and we will start a little today because it is a complicated thing and we won't finish today, and we will continue into the next lecture. So, stability analysis is that analysis of the system when you apply perturbation to a steady state. So, if a system, you have done this partially I believe in the control class, process dynamics and control, and we are going to use some of those things that you had learned over there. So, what is the idea of a stability analysis? The idea of stability analysis, you first obtain the steady state of the system, then you perturb the steady state slightly and you see how does the system react. Okay, how does the system react? There are two possibilities, two major possibilities, three actually, but let us say two major possibilities. One is that the system will go back to the steady state, stabilize. The other is the system will move away from that steady state, which is destabilize. And the third possibility is a minor possibility, is that the system remains exactly as you put it. You know, you perturb it and the perturbation continues, that little perturbation you gave continues like that. It does not grow, does not decay, but that is a minor possibility because that does not happen. The two major possibilities, one is the perturbation that you give decays, as a result of which, remember, the perturbation that you give decays, as a result of which the system returns to the steady state, and the second one is a perturbation that you give grows, as a result of which the system destabilizes. So, how do we mathematically analyze and understand this? So, this is what we are going to do over the next lecture. So, the method that we use is the Liapanov here, the Liapanov method of linear stability analysis for a chemical reactor, and you have probably used it in your control class. It was found by Bellew and Amundsen, this is a typo over here, AMUND, Amundsen, this should not be N, not N, AMUND, Amundsen, 1955. Amundsen, it turns out that he is known as the father of modern chemical engineering as we know it, University of Minnesota Chemical Engineering Department, which is the best in the world. He was the chair of that for 25 years, and then the chemical engineering department at University of Minnesota is known as the Amundsen Hall, and the major most important award of chemical reaction engineering is also named after Amundsen. So, he is the father of modern chemical engineering. Why I am calling it modern chemical engineering is that it is with Amundsen, he is the one who introduced, along with Bird, Stewart and Lightfoot of course, but he is the one who introduced mathematics or applied mathematics to chemical engineering, and as a result of which chemical engineering has the form that it has today. So, Bird, Stewart and Lightfoot are responsible for introducing mathematics, applied mathematics to transport phenomena. So, the way we talk about heat transfer, mass transfer and momentum transfer is because of the changes that were brought in by Bird, Stewart and Lightfoot in the 1950s, and the very famous book that they have. So, we do not look at heat transfer just in the terms of a heat transfer equipment or mass transfer as a distillation column, but we understand the basics of the system, and we understand that everything that follows, be it distillation, be it adsorption or absorption or heat exchange in a heat exchanger, everything is a product of the very basics of heat mass and momentum transfer. And if, as you have done in your transport phenomena lecture, there is a tremendous analogy between heat mass and momentum transfer. So, if you describe one set of systems, the momentum transfer equations, you can use the same systems, a boundary layer and so on, to describe heat transfer and mass transfer. So, this was the concept that was introduced by Bird, Stewart and Lightfoot to chemical engineering, and we owe it, we owe it to them. Similarly, we owe it to Amundsen, Neil Amundsen, for introducing the whole of this similar kind of approach, a very mathematical way of looking and a very basic way of looking to chemical engineering. Before that, chemical engineering is also just about using chemical reactors and getting products out, but then he introduced this whole approach, and one of the major things that he did was looking at stability. He also did introduce bifurcations and analysis, but so his two major contributions is stability analysis and bifurcation analysis, and what we study in today's lecture and next lecture is essentially a contribution of Amundsen, the linear stability analysis, and 1955. So, what we do is that we have to write the CSTR equation in an unsteady state form now. So, we looked at the steady state, we had the unsteady state equations, we wrote it before, but we did not solve it at that point of time. Now, neither are we going to solve the unsteady state equation now, but we are going to analyze the stability of the steady state using the unsteady state form. Now, I want to give you a generalized way of looking at it, and therefore, what I do is I use a vectorial analysis, a vectorial form of it. So, if you remember, we had two components, the x and the s, the cell and the substrate. Now, we write it in the vectorial form, del dc dt equals f c, and c is a concentration vector which is composed of s and x, fine. Now, similarly, just because c is a vector, f also has to be a vector, right. So, f is vector of functions, and P over here is a vector of parameters. So, P also involves a lot of these parameters, and let us chart them out. So, it includes the dilution rate, it includes the Y, the yield ratio, the Ks, Michaelis constant, the mono growth kinetic constant, mu max, the maximum growth rate, and the initial substrate concentration, fine. And so, the solution of the steady state solution would be, if I wanted to write it in mathematical form, what would it be here? F as steady state, just F as. So, we will write it like this, F CSS. So, F remains the same, CSS comma P equals 0. So, let me ask you this, so what we are trying to, let me try and explain for us. What we are trying to do is not obtain the unsteady state solution of the problem. As I said, what we are trying to do is give a little perturbation to the system and try to see how the system functions. So, what we are trying to look at is how it functions in the vicinity of the steady state or in the neighborhood of the steady state. So, as soon as I say that, so what rings a bell, rings a bell? So, I have the steady state and I am trying to look at what happens in the vicinity or the neighborhood of the steady state. So, what should I do mathematically? How? How? No, what is the theory? What is the theory that we are going to use? What is the theory used to look at deviations from anything, small deviations from anything? So, F over here, if you look at the screen over here, F at unsteady states, slight for small perturbations at the unsteady state is slightly deviated from F at the steady state. How do we quantify that deviation? What is the theory we use? What is the theory we use? You know this, you should, and I believe you know this. Taylor series expansion, right? Yeah, it's so simple when I say it. So, for Taylor series expansion, we need to figure out what this deviation is. So, the deviation is a small deviation about the steady state. Is that clear? About the steady state, that has to be very clear. First, we obtain the steady state solution and then we give a small perturbation and then look at deviations around the steady state. So, x is my deviation around the steady state, which is given as Ct minus CSS, CSS being the steady state and Ct being the current one in the presence of deviation. So, what we want to study? We want to study is, we gave a small deviation to the variables around the steady state. We want to figure out that how is the system going to behave? Is it going to blow up? Are the deviations going to grow with time, or the deviations are not going to grow with time? Okay, and we will do a linear stability analysis, which means that linear stability analysis would mean that this is a nonlinear system. What we have to do? Linearize it. Yes. So, because I wrote my x as like this, so now Ct could be written as CSS plus xt. Why am I writing in terms of xt? Just because I want to do a Taylor series expansion, fine. So, so my dxdt would be written as f as CSS plus x comma p, fine. Why do I write it? Because I want to, so what would be the Taylor series expansion of this about Cs? So, it would be f Cs comma p plus the rest of the terms. So, if this I am now showing for any term. So, if g which is the function of CSS plus x is a scalar, then and I am going to go to the vector form of that. So, I am giving you the simpler thing today, which is this Taylor series expansion in a scalar form. So, then Taylor series expansion of GSS is given as this. Okay. So, G CSS plus x is simply G at CS plus del G del CS times x del 2G del CS square. This is not, remember, one thing I want to tell you, and sometimes people make mistake, it is not del G del CSS, it is del G del C evaluated at CSS. Okay. Similarly, it is del 2G del C square evaluated at CSS and x square over 2 plus higher order terms. Now, if I am to do, quickly tell me, if I am to do linear stability analysis, how many terms should I take in the system? First 2 of the terms. So, I have to stop at x, okay, if I want to do a linear stability. As soon as I do take x square, I get a non-linear Taylor series. So, I do not want to do that, but the reason I want to do a Taylor series expansion is because it is easy to handle. If I wanted to solve a nonlinear equation, I would have actually gone and solved the full equation. Why would I do a Taylor series expansion about it, right. So, linear analysis is easy to handle and it would give me what I want. What I want is I just need to figure out the earlier initial trends, like when there is an election, people are always interested in the initial trends, because initial trends show basically most of the time what is going to happen. So, similarly here also I am really interested in the initial trends, and as soon as I get the initial trend I will have a ballpark idea of whether the system is going to decay or grow. So, I will stop here today, and from the next class what we have to start with is how to convert this. Remember, our system is vectorial, okay, our system is vectorial, and this is a vectorial form out here, and if you look at the screen. So, if you so my question is that how to convert this Taylor series expansion. In the first thing we will do is from the scalar form to the vector form, okay, and then we will continue from there. So, let us stop here and we will continue from here tomorrow morning.